orthogonality and orthonormality of the wave function. The Schrödinger equations, which are the foundation for quantum mechanics. We know that solution from them gives us many wave functions. Solution from this is a general time independent Schrödinger equation. Solution from this gives us wave functions, which we usually use psi to represent them. And from Born's interpretation, if we get solution from this equation, let's say psi n and psi m, which are solution from this equation. If we take psi n and square it with its complex conjugate, integrate from negative infinity to positive infinity, it should give us 100% probability of finding a particle within the wave function. I mean, within the small space available, which is from minus infinity to positive infinity. This is volume element, which can be the x, the y, the z, and so on. And we said that if we evaluate this and the result is 1, it means this wave function is normalized. 1 means 100% probability of finding the particle within the space. So what if we have two wave function from the Schrödinger equation? Let's say psi of n and psi of m. One operating on the complex conjugate of the other. Let's say the limit of integration is from negative infinity to positive infinity. And the result happens to be 0. We can also write it in such a way that psi of m will be the complex conjugate and psi of n will be a normal wave function. So these two wave functions are different, but finding the probability density of two of them gives us 0. Then we can say that the two wave functions are orthogonal to each other. Orthogonal to each other. Depending on which one is the complex conjugate. Here, either psi n can be the complex conjugate and psi m being the normal wave function. The same thing happens here. If psi n tends to be the normal wave function and psi m being the complex conjugate, the result of finding the probability density from negative infinity to positive infinity, giving us 0, tells us that these two wave functions are orthogonal to each other. So that is the orthogonality condition. And this is a normalization condition. Generally, for normalization, we are looking at the same wave function and its complex conjugate. So let's try to combine these two ideas, the normalization and then orthogonality condition. Well, we can say integral from negative infinity to positive infinity of psi n and then psi m volume elements. We can also write it in the other way around. On the other way around, psi n, psi m being the complex conjugate plus volume elements. So let's say this is equal to canonical delta n m. Let's decide to take one of them. So which way you write them is normal. I mean, it's okay to write them in any way. Either psi of n being the complex or psi of n being the complex. So delta nm equal integral from negative infinity to positive infinity psi n star psi m volume element, where psi n delta nm is called the Kronecker Kronecker delta. Kronecker delta. And it is defined as delta nm equal 0 for n not equal to m, and 1 for n equal to m. So this simply means that if you have two different wave functions and you are finding their probability density and the result happen to be 0, then it means that the two wave functions are not the same, right? It means that n is not equal to m. So the two wave functions are not the same. But if the probability density gives you 1, it means the two wave functions are identical. So that is what it means. So we therefore call this as the orthonormality, because we combine the idea of orthogonality and then normalization concept to arrive at this point. So this is known as the orthonormality, which is defined by the Kronecker delta. So wave functions that satisfy this are said to be orthonormal to each other. So that is what you should know here. If you integrate and the result gives you 1, it means the two wave functions are equal, identical. But if the result gives you 0, then n and m are not equal. The two wave functions are not identical. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.